Okay, so let me share the whiteboard. Is whiteboard visible to everyone?
Yes, sir, visible.
Okay. So now let me write down this. Okay, so this is what is been given in the first problem in tutorial number 9, isn't it? This is a tutorial 9. So what is been given is the monochromatic emissivity of a surface varies with wavelength in the following manner as given here in this equation. Calculate the heat flux emitted by the surface if it is at a temperature of 1500. That is what is been given. So here the heat flux or emissive power both are same, isn't it? So that we can calculate here as E, we can calculate as so in this case, if you look at it, what we can have is 0 to infinity epsilon lambda E lambda d lambda. That is what we have to calculate. Is it clear to everyone? Isn't it? We wanted to calculate the heat flux emitted. So we are interested in calculating the emissive power E with respect to the complete distribution of the wavelength, isn't it? From 0 to infinity, isn't it? So now we can put these individual terms here. So individual terms are for lambda 0 to 0.3, that we can write 0 to 0.3, isn't it? Epsilon lambda is 0, so 0 into E lambda d lambda, isn't it? This will be the first expression. Second expression will be 0.3 to 1, 0.9 E lambda d lambda, and the last term will be plus 1 to infinity, again 0 into E lambda d lambda. Do you all agree with me?
So can't we directly use sigma T raised to power 4? Epsilon sigma T raised to power 4.
Epsilon. Okay, so what you are
Epsilon
saying
into
is
sigma.
yes, that is what we are going to use. But in this case, remember, in this case, what we are having? In this case, we are this. It's not completely black surface, isn't it?
Yes, sir.
That's why emissive power is multiplied.
Okay, sir.
Correct.
Yes,
So
sir.
it's not a completely black surface. That's why emissive power is multiplied, and uh, of course you can calculate, but then that will be for a black surface, isn't it?
Yes,
That's
sir.
why we have multiplied the individual emissivities. Correct.
Sir, if emissivity is constant over all lambda, then we can use that as well, right?
No, so see, okay, you can use that. So see, that equation is derived only for a black surface, isn't it? That is
Yes, sir.
derived only for a black surface.
Yes, sir.
So in this case, uh, In this case, we are not having a black surface, and at the same time, if it is not a black surface, isn't it? Then calculating is not easy, isn't it? Then calculating is not easy, correct? So here we are doing it for a real surface, and at the same time we are doing it for a specific frequency. We are not looking for the complete frequency. This is the monochromatic emissive power, isn't it?
Yes, sir.
But the earlier equation which we have derived, sigma into T raised to the power 4, that expression is derived for a perfectly black surface and over the frequency wavelength varying from 0 to infinity, if you remember.
Yes, sir.
In this wavelength is also not 0 to infinity. Here, remember, this part is 0. This part is 0. So you are only looking at 0.3 to 1.
Yes, sir.
So what you have to do then?
Integration.
You have to do that complicated integration which we have shown earlier, isn't it?
Yes, sir.
So instead of doing that complicated integration, then you can use a F factor, isn't it? Remember, I said that whenever such complicated integration comes into the picture, you better use the F factor directly instead of solving a complicated integration, isn't it? That's what you have said. Yes or no?
Sir.
So we will use a F factor in this case. Let me just open that PPT also so that you will appreciate what I'm trying to say. Is it visible? This PPT is visible? Yes or no?
Yes, sir, visible.
PPT is visible. Okay, so here you can see we can have sigma raised to the power, sigma into T raised to the power 4 only in case of black body and when you are doing it between 0 and infinity. When wavelength is varying between 0 and infinity, but in this case, in the current case, the wavelength, remember the two factors are becoming 0, but the remaining factor which is not becoming 0 is not between 0 and infinity, correct? So we have to use the F factors like this to account that, okay? Does it make sense to everyone?
Yes, sir.
Okay, so in this case, what we will be left with is this. We will be left with E is given as 0.321, 0.9 E lambda D lambda. This equation we have to solve. So this we can represent in terms of a F factor. This we can represent in terms of a F factor. So what we will have is, in this case, what we can have is 0.9 into FB 0 to 1 minus FB 0 to 0.3. So that will be the difference multiplied by sigma into T raised to power 4. That's what we have to calculate. Is it clear to everyone? Isn't it? This is what the equation we need to use. Make sense?
Yes, sir.
Now in this case, let's put all the values here. So what we are going to get is from this what we, okay, so now we can look at the table, but for that table we have to first calculate the lambda T1 and lambda T2. So sorry, lambda 1 T1 and lambda 2 lambda 1T and lambda 2T. This is what we have to find out. So 0.3 into temperature is 1500, isn't it? Correct? So this comes around 450, let's say, and this comes around 1500. Now you can see the table for 450, the value is very low. So for this particular value, if you look at the table, F factor, this F factor comes out to be almost 0, isn't it? But how about this, the another one? In this case, you will get the F factor. You will not get directly the F factor exactly at this value of 1500, but you will get the value in between. So that F factor FB 0, 1. This comes around 0.0053 plus, if you look at the table, 0.0254 divided by 2. So we are just taking the average of the values. So this comes around 0.01535. So this is just from the table. I will just go back to the table and explain again so that you will appreciate what I'm trying to say here. Here you can see the table, isn't it? If I'm having the value of lambda t less than 450, there is no 450 value I have shown in this table. Can you see, Utkarsh?
Yes, sir.
There is no 450. So what will be the F factor value corresponding to that? 0.
0 approximately.
Correct. And the other value is what? Other value is 1500. So 1500 will be between these 1333 and this, isn't it?
Yes,
in between, sir. Here. Correct.
Yes, sir.
So I have just taken the average of these two values as a F factor corresponding to the value in between here. Okay.
Yes,
is it clear?
Yes, sir. Clear.
So based on that, we have obtained this. Okay, is it visible? The whiteboard is visible. Now the calculations are very easy. After that, once we get this, the calculations are very easy. Now we can just obtain the things as we can obtain in this case E can be obtained as 0.9 into FB01 is what? This F factor is what? We have obtained that as 0.01535 minus 0 into sigma is Boltzmann constant is 5.670 into 10 raised to power minus 8 into temperature is 1500 raised to power 4. So ultimately this calculation comes around 3965.5 watt per meter square. Is it clear? Hello?
Yes, sir. Clear.
So this is the answer for the first part. Okay. This is the answer for the first part. Let's look at the second part. Second part is, again, let me copy the statement as it is. Okay, so this is the second question. In the second question, what is being given is, let me just write down that part also. You have been given additionally E is given as 0, 750 and 0. This is watt per meter square micrometer. Okay, and the range is given as 0 lambda 2 micrometer. This micrometer is there, and this range is given as 2 lambda 8 is given here, and the last one is, maybe I'll just write it again. So this is micrometer. So basically this is given as 0 lambda 2. This is given as 2 lambda 8, and this last one is given as lambda greater than 8. Okay, and in addition to that, the absorptivity is given. Alpha lambda is given. Alpha lambda is given as 0. 1.5 and 0, and this is given between 0 lambda 4 lambda 8, and the last one is for lambda greater than 8. Okay, so these are the things given in the problem. What is being asked is the variation of the monochromatic irradiation incident on the opaque surface. Opaque surface means what? The transmissivity is not there. There is no transmission. Okay, so opaque surface, only the reflection and emission is there. Okay, and the monochromatic absorptivity of the surface with the wavelength is also given, isn't it? Calculate the absorbed radiant flux, the absorptivity and reflectivity of the surface. This is what is being asked in the question. So what we have to calculate is absorbed radiant flux. Now absorbed radiant flux will be what?
Alpha lambda E d lambda.
Absorbed radiant flux. So absorbed radiant flux, we can write this as, let me just scroll a little bit up. So absorbed radiant flux, we can have this 0 to infinity E lambda d lambda. Do you agree with me?
Yes, sir.
Isn't it? So we will have absorptivity multiplied by the total emissive power, and we are finding out with respect to a particular wavelength, that will give me the absorbed radiant flux. Okay, so in this case now we can write down this in terms of the different values of epsilon lambda and E are given. So we can write this as 0 to 2 alpha lambda E lambda d lambda. This will be a first term. Second term will be 2 to 4 4 to 8 alpha lambda E lambda d lambda, and the last term will be between 8 to infinity alpha lambda E lambda d lambda. Now if we put the values here in this equation, what we are going to get is, if we put the values in this equation, if you put the values in this equation. So alpha lambda, you can see that the alpha lambda for the 0 to 2 is what? Just 1, isn't it? So 1.
Yes, sir.
0 to 2. Okay, maybe I'll just directly write it instead of wasting too much time on this. So 1 into 0 into 2 minus 0, that is what we are going to get for the first. Second case, what you are going to get is 1 into 750, 4 minus 2 plus 0.5 into 750,
4 to 8.
8 minus 4, correct?
Right.
And the last term will be again
0.
0, isn't it?
Yes, sir.
So ultimately this term becomes 0 and the last term becomes 0. So only these two terms are remaining. So if we calculate the value, this comes around 3000 watt per meter square. This comes 3000 watt per meter square. Okay. Now what is been asked in the question? In the question, what is been asked is calculate the absorbed radiant flux and absorptivity reflectivity, isn't it? Correct. Now, how much is the incident radiation? This is the radiation absorbed, isn't it? Correct. This is what the radiation absorbed. What will be the incident
Yes,
radiation?
sir.
Incident radiation in this case will be given by what? So incident radiation, we just calculate this, isn't it? 0 to infinity d lambda d lambda, isn't it?
Yes, sir. Yes, sir.
That's what we have to calculate. So that comes around 758 minus 2, correct? So this comes
Yes,
around
4500.
4500
Yes, sir.
watt per meter square. Now, once we got this, we can now calculate the absorptivity. See, earlier the absorptivity given with respect to the individual wavelength, but now we wanted to calculate what will be the overall adsorptivity. So overall adsorptivity will be given by what?
3000 by
The incident radiation
4500.
absorbed divided
Yes,
by
sir.
the total incident radiation, isn't it? So that is
Yes, sir.
4500. So this comes around 0.667.
0.67.
Correct. This is the absorptivity.
Yes, sir.
Now alpha plus transmissivity plus reflectivity, this should be equals to 1, isn't it?
Yes, sir.
Surface is
Opaque.
Opaque, isn't it?
Yes,
Surface
sir.
is opaque. So for a opaque surface,
Transmittivity is 0.
so transmissivity should be
0.
0, correct. So alpha plus rho should be 1, isn't it? So rho will be given by 1 minus alpha. So 1 minus 0.667 should be the reflectivity. So reflectivity comes around 0.333. Correct?
Yes, sir.
This is the answer for the second part. Now let's look at the third part. Let me scroll a little bit up. Copy the statement. Let me copy the statement.
Third part was the absorbed radiant flux.
So I'm copying here so that somebody who is looking at this this file, he don't need to open the multiple files together, isn't it? So that's why I'm trying to copy here. Okay. Okay, so let me just give the statement here. So in this case, what is been given is, this monochromatic emissive power is given, isn't it? That given as 0, 2500, 4000 and 2500 and 0. So 5 values are given between 0, lambda, 0.5 micrometer. This is given as 0.5 micrometer, lambda, 1.5, and this 1.5 lambda, 2.5, and this last one is 2.5 to 3.5, and finally lambda is greater than 3.5 micrometer. This is what is given. Okay, now we wanted to find out also here, calculate the rate at which the radiation incident on the per over the solid angle included by, so here this solid angle is included by 0 to lambda, 0 to psi, this is pi by 3. So psi is varying between 0 to pi by 3, whereas phi is varying between 0 to 2 pi. Okay, so for this case we have to calculate the rate at which the radiation is incident on the surface per unit area. So basically what we are interested in calculating is, we are interested in calculating the
incident flux.
So we wanted to calculate this E, which can be given by 0 to infinity. So this is the summation over the lambda, isn't it? But also yes, the incident radiation are also varying along the psi and phi direction. So we have to represent that 0 to 2 pi is nothing but the psi is varying, and between 0 to pi by 3, 0 to 2 pi phi is varying, and 0 to pi by 3 psi is varying, isn't it? And we have to write down the this as I lambda sin psi d psi d phi. This is what should be the equation, and d lambda. Now this equation we have taken as it is from our earlier calculation. I mean, I can open that directly. Let me just open the radiation 2. So then you will appreciate from where this equation is coming. So let me just share the file. Is it visible?
Yes, sir, visible.
So you can see that IB lambda we have calculated as, so see, EB lambda is what we have to integrate over the wavelength, isn't it? But EB lambda will be given by what? IB lambda d omega, and d omega is nothing but what? Solid angle. So that d omega solid angle comes around sin psi d psi d phi. isn't it? So we will be integrating between 0 to 2 pi, 0 to pi by 3, because in this question pi by 3 is given, isn't it? IB lambda sin psi d psi d phi, correct?
Yes, sir.
So this is what the equation we are using in our calculation. So whiteboard is visible.
Yes, sir, visible.
Okay, so let me just scroll up a little bit. So now in this equation, this I lambda is nothing but what? Intensity is spectral intensity, and the spectral intensity is given by what? The spectral intensity I lambda is given by the spectral intensity. The equation for the spectral intensity is E lambda pi cos psi, isn't it? That's what the equation is. So we can put it here in this equation. So E is given 0 to infinity in the bracket 0 to 2 pi 0 to pi by 3 E lambda by pi sin psi cos psi d psi and d phi and this entire bracket is d lambda. Okay, now this integration we can solve. So if we solve this integration, what we get is, so see this d phi is there. So d phi, this phi is varying between 0 to 2 pi. So this d phi, integration of d phi will be 2 pi, isn't it? That will be just 2 pi. This epsilon, lambda and pi, we can take it here, isn't it? Before d psi, isn't it? So what we get here is 0 to infinity E lambda by pi we have taken common as it is, isn't it? Multiplied by 2 pi, because this d phi is integrated and that gives me 2 pi. 0 to 2 pi integration of d phi between 0 to 2 pi gives me just 2 pi, isn't it? And the remaining term is sin psi cos psi d psi integration over 0 to pi by 3. That gives minus cos 2 psi by 4 0 to pi by 3 and d lambda. So if you rearrange all the term, what you get here is 3 by 4 integral 0 to infinity E lambda d lambda. This is what you are getting. Now once we get this, now the calculation becomes very easy, isn't it? Now calculation becomes very easy because this E lambda is already given, isn't it? So this E lambda we can put it, isn't it? E lambda values are given for various value of lambda, isn't it?
Yes, sir.
So this comes around 3 by 4 as it is, and for a different values of E lambda, we can get 1.5 minus 0.5. This will be first term. Second term will be 4,000. 2.5 minus 1.5, and third term will be 2500. The term will be 3.5 minus 2.5, and the other two terms will be 0. So by putting all these terms we can calculate. This is 2500. This is 2500. Okay, so what we get is 6750 watt per meter square. This is what the answer we are expected to get in this case. Is it clear to everyone?
Yes, sir.
Now, why we have done this entire procedure? Why we have not integrated directly E lambda, D lambda? Remember here the solid angle is very important, because that is what in the question what is given is we wanted to calculate the values for the given solid angle, isn't it? That's why we have calculated this E lambda in terms of the solid angle first. Right? Got the point?
Yes, sir. Yes, sir.
So that is the small difference one has to remember. Otherwise we get confused. Okay, so this is all about the tutorial number 9. Let's move to tutorial number 10. Okay, this is about the tutorial number 9. Let me just copy the question for tutorial number 10. Just let me scroll a little bit up. So now tutorial number 10.
Sir, in the last problem, should we compute E or I?
What is the question? Calculate the rate at which the radiation is incident on the surface per unit area. Isn't it?
Yes, sir.
So we are calculating just calculating what will be E. That is coming from
Okay, sir.
the different thing. Okay.
Yes, sir.
But since the not everything will be only okay, so that will be E from some other surface, isn't it? So see here E lambda is given from the diffuse radiation, but not all these E lambda will be incident on the surface, isn't it?
Yes, sir.
Maybe I'll just scroll a little bit up so that you can appreciate what I'm trying to say. So in this problem, what is given is this epsilon lambda is given, which is nothing but the spectral distribution of diffuse irradiation falling. This is the irradiation falling, but not everything will be intercepted by a particular surface. So out of these, only the part of that will be intercepted by a surface depending on the solid angle. Isn't it?
Yes,
so
sir.
that's why we have represented this epsilon lambda in terms of solid angle first, isn't it?
Yes, sir.
Correct. That is the reason why we have done this, and why we have not done directly E lambda, D lambda. If this would have been completely intercepted by the surface, then we would have taken E lambda, D lambda, isn't it? Integration
Yes.
over 0 to infinity E lambda, D lambda. Correct. But not everything from this E lambda will be intercepted by a given surface, and therefore we have to include this solid angle here. So in a way, this the interesting thing to note down is this 3/4 which we are getting here. What this 3/4 will represent?
So this amount of E lambda, D lambda, which is
nothing but a shape factor. We are not explicitly naming it, but it's a shape factor. Got the point?
Yes, sir.
This is nothing but the shape factor which we have obtained as a 3/4 here by considering the entire solid angle and other things. Correct?
Yes, sir.
Okay, all right. Okay, so let me just go back to the new problem. This is a very interesting problem. Okay, what is been given here is, maybe I will explain the situation first. So there is a bulb. Let me draw a bulb first so that you will appreciate what I'm trying to say. There is a bulb. This is a bulb. Inside this bulb there is a filament. This is the filament. Okay. Now the surface temperature of this bulb here, surface temperature on this entire circular spherical bulb is temperature is 100 degrees Celsius. Okay, 100 degrees Celsius. What is the temperature of this filament? Temperature of this filament is 3000 Kelvin. 3000 Kelvin. Okay. Now this is the typical situation which we see in our day-to-day, day-to-day experience in our house, isn't it? You all might have seen those standard filament type of bulbs earlier. Have you?
Yes,
or no?
sir. Yes,
So
sir.
what happens there? That filament is, emitting the radiation, isn't it? And outside of that filament, there is a bulb which is made up of a glass. Correct. So that glass is getting heated to 100 degrees Celsius. Now this outside bulb is made up of a glass. So clearly, which type of radiation will be causing the heating of this outside glass which is there? What type of radiation is leading to the heating of this? Remember, the temperature here is not an ambient temperature. If you just touch that bulb, you will see that that bulb is hot, isn't it? Yes or no?
Yes, sir.
So what makes this bulb outside here hot? Remember, this bulb is going to be a transparent bulb, isn't it? So all the
Yes,
radiation coming out from here should pass through this bulb, but still this bulb getting heated and the temperature increases to 100 degrees Celsius. Outside ambient temperature here is 30 degrees Celsius, isn't it? TA here is 30 degrees Celsius. That is what given. This is T surface and this is T filament. Correct? So what makes this body of this glass body of the bulb, what makes this glass body of bulb to increase its temperature?
Absorptivity probably.
It absorbs. But what type of radiation it absorbs? It absorbs the radiation which is not there in the visible range. Okay.
Yes.
So glass surface absorb radiations beyond the visible range. Do you agree with me when I am saying this statement? The glass surface absorbs the radiations beyond the visible range. Remember, this glass is a transparent. When I'm saying a glass is transparent, what it means? All visible radiation will easily pass through it. Do you agree with me?
Yes, sir.
Okay. So when I'm saying this glass which is outside here, this glass body is transparent, which is there, isn't it? What it means is it will let all the visible radiations to pass through it, and only those radiations which are beyond the visible range, part of that get absorbed. Not all of that get absorbed, only part of that get absorbed. So whatever the radiation beyond the visible range is there, fraction of that get absorbed at this glass surface, and therefore the temperature increases to 100 degrees. Do you agree with me?
Yes, sir.
Now what is been asked in the question? In the question, what is been asked is transmissivity of this glass for a higher wavelength radiation. This is what is asked. What will be the transmissivity of this outside glass for the higher wavelength radiation? That is what is been asked. Okay. So what we have to do is we have to first calculate how much is the radiation outside this visible range which are generated by this filament. Correct. And then we have to calculate how much is the radiation responsible for increasing the temperature to 100 degrees Celsius for this glass. And that particular radiation divided by the total radiation which are beyond this visible range, that will give the transmissivity. That will give the absorptivity of this glass, isn't it? And 1 minus absorptivity of the glass will be the transmissivity. Correct? Because there is no reflection here. Correct? Do you agree?
Yes, sir.
Okay. So now what is been given in the problem is there is a 14 watt incandescent electric bulb. 14 watt incandescent electric bulb. So what is been given is whatever the total energy radiated from this filament is what? 40 watt. Do you agree?
Yes, sir.
Some of that will be falling in the visible range and the remaining one will be falling in the invisible range. Correct? What is the visible range? Visible range is up to visible
range nanometer
is up to visible range is up to 0.78 micrometer wavelength. Isn't it? It is 0.3 to 0.78, but we are neglecting even the initial 0 to 0.3. That also we are considering as a visible range for a sake of simplicity. We can solve the exact problem also by taking 0.3 to 0.78. Doesn't matter. Make sense, Utkarsh?
Yes, sir.
Okay, all right. Let me scroll little bit up. So 14 watt incandescent electric bulb is there, which is generating the radiation of 40 watt. Now, so see, okay. So 40 watt heat is generated here, isn't it? Now some of that heat will be, will be in a visible range, and some of that will be in an invisible range. Out of that invisible range, whatever the radiation which is there in the invisible range, part of that will get absorbed on this bulb. And this bulb being at a temperature of 100 degrees Celsius, it is going to emit the radiation. It is going to emit the radiation, isn't it? And also it is going to dissipate the radiation by convection. Both the things are going to take place. So if I consider only this bulb surface here, if I only consider this bulb surface here, this surface here, it is going to radiate. So both the phenomena are going to be there, isn't it? If I look at this, this will have radiation as well as convection, isn't it? So both we have to account. So let us first, account the radiation. So what will be the amount of radiation emitted by this glass surface? So QR will be given by A epsilon sigma T1 raised to power 4 minus, let's say this is okay, maybe I'll just put it TS raised to the power 4 minus TA raised to power 4. This will be the net radiation emitted by the glass bulb. Do you agree with me?
Yes, sir.
Now what will be area in this case?
4 pi.
4 pi r square, isn't it? So I can take that as a pi d square, isn't it?
Yes, sir.
Correct. So pi d square is pi 0.06 square. That is the area, isn't it? What is the emissivity given in the problem? Emissivity given in the problem is surface having the emissivity of 0.8, isn't it? So 0.8 is multiplied here. What is the sigma value? 5.2 0.67 into 10 raised to power minus 8, isn't it? TS is 373, isn't it? We have to take it in Kelvin, isn't it? So 100 degrees Celsius is 373 Kelvin minus 30. So 30 is going to be 304.
303.
273 plus 30, how much?
303.
303. So what will be the value? So this value comes around 5.6 watt. Check whether you all are getting. Okay. Is it clear?
Yes, sir.
Now there is another very interesting thing. There is a convection taking place. Convection is also taking place outside because this wall is at 100 degrees Celsius and outside the air is there. So that air is going to take some amount of heat by convection, isn't it? So how we can account that convection, natural convection here? For a natural convection, first we have to calculate the average temperature. So average temperature will be what? 100 plus ambient temperature is 30 divided by 2. So that comes around 65 degrees Celsius. 65 degrees Celsius. Then we have to account all the properties of what? Properties of air at 65 degrees Celsius, isn't it?
Yes, sir.
Do you agree?
Yes, sir.
So properties of air at 65 degrees Celsius. So what we can have at 65 degrees Celsius is we can get beta. Beta is just 65 plus 273. So this comes around 0.00296. Okay. Then kinematic viscosity comes around 2 into 10 raised to power minus 5 meters square per second. So all these are given backside of the book. Prandtl number is 0.7 and thermal conductivity is 0.0295. So now we can use the formula here as the Rayleigh number based on the diameter of the bulb, that can be given as G beta delta T. So we will have TS minus TA D cube Prandtl number divided by nu square. So we can put all the values here. 9.8 multiplied by beta is 0.00296. 100 minus 30. D cube is 0.06 cube into Prandtl number is 0.7 and divided by this entire thing is divided by nu square. So that is 2 into 10 raised to power minus 5 square. So what we get from this equation is Rayleigh number in terms of the diameter comes around 15.4. Now once we get the Rayleigh number we can, the Rayleigh number is not 15.4. Rayleigh number comes around 7 into 7.67 into 10 raised to power plus 5. That is what the Rayleigh number we are getting. So yes, from this Rayleigh number, then we can calculate the Nusselt number. So Nusselt number, we can use the correlation. So Nusselt number is given as HD by K is given as 2 plus 0.589, Rayleigh number raised to the power, 7.67 into 10 raised to power 5 raised to the power 1/4. So this is the equation which we have seen already for a spherical type of thing. This is what the equation we can write. So this is 0.469 divided by Prandtl number, which is 0.7, and this entire thing raised to the power 9/16, and this bracket is raised to the power 4/9. So this comes around 15.4. So this equation is, if I go back, this is the same equation which we have seen in the forced convection. Let me just open that so that you will appreciate. So let me open natural convection. We have used this equation. Okay. So Utkarsh, just check whether it is visible to everyone or not. Remember, this is the equation we are using for convection, forced convection from a sphere. Can you see?
Yes, sir, visible.
This is the same equation which we are using here. So with this equation, we can calculate what will be the Nusselt number, and from Nusselt number we can calculate the
Heat transfer coefficient.
Correct. So from this we can, again, this Nusselt number will be given by what? This Nusselt number will be given by, so here H into D is 0.06 divided by K. K is, again, we have defined that as 0.0295. Okay, so with this, if we back calculate the H comes around 7.58 watt per meter square degree Celsius. This is what we are expected to get. Now once we have obtained H, now we can calculate what will be the heat dissipated by a convection, isn't it? So heat dissipated by convection, so QC can be obtained as HA delta T. So HA delta T in this case is 7.58. Area will be what? Pi D square, isn't it?
Yes, sir.
Into 0.06 square into 100 minus 30. So check
Yes,
what
sir.
value we are getting.
Approximately 6.
Approximately 6 watt we are getting.
Yes, sir.
So approximately the 6 watt is the value we are getting. So 6 watt is the convection, heat taken by convection, and almost 5.6 we have obtained from using the radiation. So total heat dissipated is what? Total
11.6.
heat dissipated will be given as 6 plus 5.6 watt. So this total is 11.6. Okay, let me just scroll a little bit up. So now out of these 11.6 watt, okay, so this 11.6 is the total heat dissipated, but we have to find out how much is the heat incident on the surface, isn't it? So see, all the visible range radiation will pass through, but all the invisible range radiation will be intercepted by this glass surface, isn't it? And we are assuming that the invisible range is starting from 0.78 micrometer onward, isn't it?
Yes, sir.
So invisible range is 0.78 to infinity, correct? Right? Micrometer.
Yes, sir.
Now we have to find out how much will be the total amount of radiation in this range. So how we can do? We have to first find out the F factor. FB 0 to 0.78 we have to find out. So 0 to 0.78, this F factor we have to calculate, correct? So again we can, so how we can find out temperature? Lambda into T we have to first find out, correct? So lambda in this case is 0.78 into what is the filament temperature is given?
3000 Kelvin.
3000 Kelvin. So this total becomes 2340 micrometer Kelvin, correct? We can go back to the table. We can go back to the table. Let me just open that. We can go back to this table, and 2340 is what we are looking at, isn't it? 2340 will be here in between somewhere, isn't it? Can you see?
Yes, sir.
So that comes around 0.1734 or something. Almost that we can get. 0.1734 or something, that around that you will get, correct? Is it?
Yes, sir.
So we can get here, what we can get here is, from this we can get F factor FB 0 to 0.78, that comes around 0.1734. Okay, so this is between 0 to 0.78, but what we are interested in, we are interested beyond, correct? Isn't it? We are interested beyond 0.78. Only beyond 0.78 will be intercepted by a glass surface. Below 0.78, anything will pass through the glass surface because that is a visible range. Yes or no?
Yes, sir.
So that means the amount of heat radiation intercepted by a glass surface will be given by what? That will be given by radiation intercepted by glass. Radiation intercepted by a glass will be given by what? 1 minus 0.1734, isn't it? Multiplied by how much is the total radiation? 40 watt multiplied by 40.
Yes, sir.
Isn't it? So total is 33.06 watt. This much radiation will be actually intercepted by the glass surface. Out of this 33.6, how much will be used, will be absorbed by the glass surface? Whatever the radiation emitted and whatever is the radiation dissipated by convection, isn't it?
Yes, sir.
So that means out of these, the radiation which is transmitted directly will be given by what? 33 minus 33.06 minus 11.6, isn't it? This is, see, 11.6 is adsorbed, so whatever is the remaining is transmitted, correct? Total invisible radiation transmitted. So this will be 21.46 watt. Do you agree?
Yes, sir.
So what will be the transmissivity now? Transmissivity for invisible radiation, that is what the question is. So transmissivity will be 21.46 divided by whatever is the incident radiation falling on this, isn't it? Invisible range 0.6, correct? So this comes around, the transmissivity comes around 0.65. This is the answer. This is the final answer. Is it clear? Is it clear?
Yes, sir. Clear. Yes, sir.
So question is slightly tricky, but I think I have given the explanation which is easier to follow.
Yes, sir.
Export. Let me just export this. High resolution. Export. Just a minute. Let me export this and save because this is becoming. Okay. So let me just share this, download. This is tutorial number, tutorial 9 and
10.
Tutorial 9 and 10. So let me open it here in some other Think, let me check whether it is opening. Okay, this is clearly visible. Yes, good. Because somehow this Microsoft thing got updated today, so I was not sure whether it is coming well or not. So can we continue with the next tutorial? So then we do not require any more tutorial. One last tutorial is there that we can do it in the tomorrow's class. So tomorrow's class will not be a long class. We can complete it in the given time. We are almost done with everything. Tutorial
Yes,
9 and 10 I have updated. Tutorial 9 and 10 is updated, is it? Just a minute. Tut 1, tut 2, tut 3, 4, 5, 6, 7, 8. Not updated. Upload. Download. Somehow this. Just a minute. Let me check this. Somehow this class material. Where it is uploaded. Okay. All right. So let me open this whiteboard again and let me open the new whiteboard. Okay, so can we do a next tutorial? Is it possible, Utkarsh?
yes, sir, possible.
Okay, all right. So next tutorial is okay. Let me just copy the statement and then and 10. So let me just take that off. Let me open the another one. Microsoft. Somehow that the previous file was creating a lot of lag, so just open the new one. So in the next tutorial, so what is been given is the water at the rate of 4 kilogram per second is heated from 38 degrees Celsius to 55 degrees Celsius in a shell and tube type heat exchanger. The water is to flow inside tubes of 2 centimeter diameter with an average velocity of 35 centimeter per second. Hot water available at 95 degrees Celsius and at the rate of 2 kilogram per second is used as heating medium on the shell side. If the length of the tubes must not be more than 2 meter, calculate the number of tube passes, the number of tubes per pass, and the length of the tubes per one shell pass, assuming U naught equals to 1500. This is a very important example. Important example in the sense that how to design the heat exchanger using the LMTD method is what explained in this. Okay. Okay. So let me just start with that. Let me just copy the question as it is.
So the board is not visible.
Board is not visible, it will be visible. Just a minute. Let me just open. Is it visible now?
Yes, sir, now it is visible.
Okay. Okay, so what is been given here is, let me just draw the figure first. So then you will be able to understand things. Okay, so there is a shell and tube heat exchanger. There is a shell and tube heat exchanger like this. Okay, so one fluid is flowing through and coming out, and then there are different tubes are there. Maybe I'll just show different tubes. There are different tubes are there. Okay. Now what is been given is water at the rate of 4 kilogram per second is heated. So water is coming in from this direction, going out from this direction. This is given as 4 kg per second. Heated from 38. So this is 38 degrees Celsius to 55 degrees Celsius. In a shell and tube heat exchanger, the water is to flow inside the tube of 2 centimeter diameter with an average velocity. So V average is given as 35 centimeter per second. The hot water is available at 95 degrees Celsius at the rate of 2 kg. So this hot water is at 95 degrees Celsius is coming in and going out at THO. So this is THI. This is TCI, and this is TCO. Okay. The flow rate is given here is 2 kg per second. 2 kg per second is the flow rate given. Overall heat transfer coefficient in this entire thing, U is given as U naught is given as 1500 watt per meter square Kelvin. This is given. Okay. Now what we wanted to find out, how many tube side passes one should use. That is what the question is. It's a very important question. How many tube side passes one should use? And also what we have to find out is, so why this question is important? This question is important because the length, maximum length allowed is 2 meter. If my length of the tube is going beyond this, then I have to increase the number of passes in order to make sure that the heat exchanger becomes compact and we can fit into a 2 meter length. That is what the idea is. So number of passes here is very important. Okay, but we can start the calculation, start with the assumption that one shell side and one tube side pass. Now with this assumption, let us start solving this problem. Okay, is it clear, Utkarsh, what we are saying?
Yes, sir.
So we have just assumed that there is a one shell side pass and one tube side pass. Now in one shell side pass and one tube side pass, that means first let's calculate Q. So Q in this case will be given by what? So Q will be given by whatever the amount of heat released by the cold fluid. So that is given as MC CPC TCO minus TCI, isn't it? That is the heat gained by the cold fluid, correct? And
Yes,
it
sir.
should be equals to the heat released by the hot fluid, isn't it? So MH CPH THI minus THO, correct? Yes or no? Now this MC,
Yes, sir.
CPC, TCI, this everything is known to us, isn't it? So we can put these values here, isn't it? So MC is 4, CPC is 4.14186, that is the specific heat of the water. Let's assume that specific heat of the water is constant to 4186 at both the temperatures. So CPC and CPH both are same, isn't it, in a way? TCO is given as 55 minus 38, correct? Isn't it? So this comes around 284.65 into 10 raised to power 3 watt, and that should be equals to MH. MH is how much is the hot water flow rate? Hot water flow rate is 2
kilogram per second
into again 4186. THI minus TH naught. So THI is given as
95 degrees Celsius.
95, and THO is unknown. So from this equation we can calculate THO, correct? So THO comes around 61 degrees Celsius. That's what you can get it by rearranging, correct? Is it clear? Now
Yes,
once
sir.
we know THO, so all the terminal temperatures are known, isn't it? All the terminals TCO, TCI, these were already known. THI was already known, but THO was unknown. So now all the terminal temperatures we know. So from this we can calculate LMTD. So delta T LMTD will be what? Delta T1 minus delta T2 divided by ln delta T1 by delta T2, correct? Now what is delta T1? Delta T1 will be THI minus TCO, because counter current contacting is there, isn't it? THO minus TCI. This you can see also in the figure. Ln THI minus TCO divided by THO minus TCI. So this you can confirm also here, isn't it? If you go back
Yes,
at the top, so this is what we are going to see. Here you can see
yes, sir.
THI. This is a THI minus TCO. This is the end one, isn't it? This is the end one. So this is 1, this is 2. So at 1, the temperature difference will be what? THI minus TCO.
I minus
This will be
TCO.
delta T1. Correct. And here what will be delta T2? Delta T2 will be
THO minus TCI.
THO minus TCI. That is what we have used. Correct. So with this delta T LMTD we can calculate. We can put all the values here. So if you put all the values here, what we get is 95 minus 55 minus 61 minus 38 divided by ln 95 minus 55 divided by 61 minus 38. So this comes around 30.72 degrees Celsius. That is the LMTD. Now once we know the LMTD, we can calculate the area. So area is Q is also can be written as UA
U0 into
delta
A.
T LMTD.
Yes, sir.
Isn't it? So area we can calculate as Q divided by U delta T LMTD. Q we have already calculated, isn't it? That is calculated 284.65 into 10 raised to power 3. Divided by U is already given in the problem 1500 into delta T LMTD we just calculated 13.72. So this comes around 6.177 meter square. This is the area. This is the heat transfer area. Heat transfer area. Okay. Now in the problem, what is been given is what is given in the problem. In the problem, the velocity of the cold fluid is given. Velocity of the fluid which is flowing through the tube is given, isn't it? So mass flow rate for the fluid flowing through the tubes. Mass flow rate is given by what? Mass flow rate is given by what? It is given by
Rho into
rho
area into
into area
velocity.
into velocity, isn't it?
Yes, sir.
Correct. So 4 is given as rho. Rho is what? 1000, isn't it?
Yes, sir.
Into velocity. Area into velocity will be given by what? Area will be multiplied by A as it is, multiplied by velocity is given as 35 centimeter per second. So that is 0.35 meter per second. So from this we can calculate area. So area is going to be 4 divided by 1000 into 0.35. Note that this area is not the heat transfer area. This is the area for the flow area. This is a flow area. Don't get confused with this. This is the flow area. So flow area comes out to be 0.011429 meter square. Isn't it? This is what we are getting.
So flow area is the total area of the pipe.
So flow area is the flow area available in the tubes.
Yes, sir.
Flow area is nothing but the area available for the flow in the tubes. So now this flow area is given by what? This flow area is given by number of tubes multiplied by area of one tube.
Yes, sir.
One tube, isn't it? So that is given as n into pi. What is the flow area? Pi d square by 4. Is it correct? Isn't
Sir,
it?
should it be 2 pi RL?
So see, 2 pi RL is okay. So note that this is the tube. Correct?
Yes,
So
sir.
when we are looking at the heat transfer, then the surrounding
Oh,
area we are taking. When we are looking at the
yes,
heat
sir.
transfer. But when we are looking at the flow, then this
Cross-sectional area.
cross-sectional area becomes important. So
Yes,
now
sir. Yes,
this
sir.
area is the cross-sectional area we are talking about, this area of the one tube. So that
Yes,
will be
sir.
pi d square by 4, correct? And
Yes, sir.
diameter of each tube is already given. So n into pi into d is what? 0.02 square. Diameter is given divided by 4. So we can calculate, and this area is given as 0.011429. So from this we can calculate n. So n comes around 36.38. Do you agree? So what does it mean? It means that in this particular heat exchanger, 38 tubes, 36 tubes we have to use. Okay, so number of tubes should be used. Number of tubes should be used. Number of tubes should be used is 36 approximately. Correct? Now,
Yes,
if
sir.
I know the number of tubes are 36, now I can calculate the area. Heat transfer area will be given by what? Heat transfer area will be given by what? N into pi dl, correct? Because now pi dl is the
Yes,
heat
sir.
transfer area, correct? And heat transfer area we have already calculated above. If you see, heat transfer area we have already calculated. This is the heat transfer area, isn't it? 0.6.177 meter square, isn't it? Do you agree? So pi
Yes,
dl
sir.
is the heat transfer area for one tube. How many tubes are there? There are 36 tubes. This length we don't know, unknown, isn't it? So 36 into pi dl, that should be the total heat transfer area. Do you agree? Does it
Yes,
make
sir.
sense, Utkarsh?
Yes, sir.
So this should be 6.177, isn't it? So n is 36 multiplied by 3.14 into diameter is 0.02 into L is 6.177. So we can back calculate the value of L. So L comes out to be in this case L comes out to be 2.731 meter. So what does this gives me the information? This information gives me this information basically tells me that if I use a single pass heat exchanger, then my length will be 2.731, but the maximum length available for me is just 2 meter, isn't it? That is what is given in
Yes,
the
sir.
problem. So
Yes.
what I can do now, I have to go
Multiple
back to my
passes.
assumption and I have to use the multiple pass in tube side
Yes, sir.
so that my heat exchanger becomes compact, isn't it?
Yes, sir.
So now, since length is greater than 2.731 meter, one should go for one shell side and two tube side passes. Okay. Now for two tube side passes with same number of tubes. So with this, let's do the calculation now. So with this now, when we are using two tube side passes, then it is not the, remember when multi-pass heat exchanger are used, then we need to use the LMTD correction factor, isn't it? Correct?
Yes, sir.
For multi-pass heat exchanger, LMTD correction factor need to be used. So for that, what we have to do? We have to first calculate this quantity. TC is given as TCO minus TCI. If you remember this is similar to efficiency, which I explained in the last class, TCI. And the second quantity is R. So that is given as THI minus THO divided by TCO minus TCI. So we can calculate this. All the terminal temperatures we already know. So we can put this as 55 minus 38 divided by 95 minus 38. So this comes around 0.3, and R is given as 95 minus THO is 61 divided by 55 minus 38. So this comes around 2. Once we know TC and R, then we can look at the tables in the book. Tables in the book are there. So there are different tables are there in the book. If you go back chapter number. So in the heat exchangers, there are different tables are given. So these different tables one can use. If I look at page number exactly. Exactly, I will let you know. Okay, so these tables are present in 292, page number 292. These are the different tables you can see. From these tables, depending on whether you are looking at 1-2 shell and tube heat exchanger or 2-4 shell and tube heat exchanger, there are different tables are there. So we can identify from tau C and R, we can identify the F factor. Also a analytical expression I have given in the slides. So from that we can find out the FT factor, and FT factor in this case comes out to be, if you look at the table or the analytical expression, the FT factor in this case comes out to be 0.9. So with this FT factor, then again we have to calculate the area A dash. So area A dash will be given by Q U FT delta T LMTD, isn't it? So the difference between this equation and the earlier equation is, in the earlier equation we have not used the FT factor, because in the earlier equation we had one shell pass and one tube pass. So there we don't require a FT factor. But in this case, since in this case the two tube side passes are there, so this is a multi-pass heat exchanger, and therefore this FT factor has to be used. So we can use all the values exactly whatever we have had earlier. So this 284.6 into 10 raised to power 3. U is 1500. FT factor is 0.9. And delta T LMTD factor we have already calculated earlier. So that is 30.72. So with this, the new area value comes, new heat transfer area. Heat transfer area new. So new heat transfer area comes out to be 6.863 meter square. Now with this we have to check whether we are satisfying the condition or not. So this area A dash should be what? This should be equals to 2n pi dl, isn't it? Because two pass is there, so in one pass n number of tubes are there. So since two pass are there, there will be 2n pi dl, and pi dl is the area for each tube, isn't it? So 2 into 36 into 3.14 into diameter is 0.02 into L. And this area is 6.863. So with this we can calculate L, and L comes around 1.517 meters. So clearly this is less than 2 meters. So this design is acceptable. So the new design is acceptable. The new design is acceptable. So new design is acceptable means number of passes will be tube side, and number of tubes will be 36. This is the answer for the question. Is it clear, Utkarsh?
Yes, sir, it's clear.
Okay, so let us stop here and we will continue. Tomorrow will be the last class and we will do one tutorial, last tutorial there in the class itself. Okay.
Okay, sir.
Thank you for coming. I think you are the only person who is there for 2 hours. Thank you so much. I think others are. Okay, all right. Chalo. Thank you.
Thank you, sir.